quickly try to say. So you see, suppose you have consider a man M1, okay, and that man may have preference for different women in different orders. So we have lots of men and women, so something. Okay. Now a stable matching is not unique. Yale Shapley finds one stable matching out of many potentially possible stable matchings. Okay. So you think about, we are not trying to find an algorithm to find all stable matchings, but we are trying to define what is meant by man optimal matching. Okay. So think of all the stable matchings that can be there, a set of all possible stable matchings. Now in each of these stable matchings, M1 must be matched to some woman. Okay. So let's say here it is matched to W8. Okay. Here it is matched to W6. Here it is matched to W10. Okay. And so on. Okay. So you look at all these W's, each of these W's out there, and you find the highest preference W that M1 got matched in any of the stable matches. If we look at the set of all possible stable matches. Okay. Again, we are not trying to find all possible stable matches. We're just trying to define what is a man optimal stable match. Okay. But if you get the set, okay, then for M1, just look at one man, you look at what M1 is paired with in each of these matchings. And then I see W8, W9 is not here. So I don't know what their order is, but W10 is definitely higher preference than W6 and W8. Okay. Maybe in some other matching, M1 is paired with W2, in which case W2 becomes the highest preference that it matched with, and so on. Okay. You may not find such a thing. Okay. So there may not be any stable matching where everybody is matched with their first one. Okay. But I find that what is the highest preference woman that M1 is matched with in, if I look at all the stable matches, and let that be Wi. Okay. Now I can do the same thing for M2, the same thing for M3, and so on and so forth. Okay. And for each of them, if I look at all possible stable matchings and what are they paired with, I will find a corresponding Wj, Wk, and so on. Okay. Now, so Yale Shapley finds a man optimal matching means if you look at the matching, so Yale Shapley will now find this matching. M2Wj, okay, M3Wk, and so on. So it finds a matching, and that is what is called a man optimal matching, where every man is paired with the highest preference valid partner that it could have had. Valid means it occurs in at least one of the possible stable matchings in the set of all possible stable matchings. So that is what is called a man optimal stable matching. That means for every man, okay, if I look at all possible stable matchings, what is that man paired with? What is the highest preference woman that man is paired with? Then in the man optimal matching, that man will be paired with that woman. So that is what is called. That need not be his highest preference woman. Okay. It is just the highest preference among all possible stable matchings. It is possible that does not exist any stable matching where M1 is paired with W. Okay. So that is what is called a man optimal. Similarly, woman optimal is the other way. Every woman is paired with their highest preference man among all possible stable matchings. Okay. And so we are not trying to once again find all the stable matchings, but you can prove. We are not doing that proof, even though it's an easy and interesting proof. Okay, you can take a look at it if you want. But you can prove that the stable matching out of these all possible stable matchings that Yale Shapley finds is the man optimal stable matching. Which means if the man proposes first, if men propose first. Which means that if for any man, you cannot find another stable matching where M2 is matched with somebody higher than Wj in M2's preference list. Okay. You can actually also prove that if men propose first, then Yale Shapley finds a kind of a worst optimal stable matching for women. That means a woman is paired with the worst possible out of all these things, the least preference thing man that occurs in any of the stable matches. Okay. But as I said in the lecture also, men and women are just how the men thing is proposed. So whoever proposes first, it is that optimal in this case. So is that idea clear? Once again, we are not trying to find all possible stable matches, but we are trying to prove this, that this is what a man optimal is, and then you can prove that what Gale-Shapley will find is this. Is it clear? Any questions on this one? Okay. If not, there is. I will do a couple of problems. Actually, both of them are easy, so we'll probably discuss them. But before that, do you have any questions on anything so far, or regarding the exam tomorrow or anything?
Sir?
Yes.
So you said that if the tab is closed, then it can't be submitted again.
What is that?
For the exam tomorrow, after opening the question, if the tab is closed somewhere, then it can't.
No. See what happens is, okay. Why don't I give you a demo? Nah, I don't want to give you a demo. Okay. I don't want to. Oh, we can give you a demo from my test. Okay, fine. So this was your dummy quiz. Okay. So you get the link. So you are in this tab. What happens is it opens in the same tab. Okay, now you will download the PDF. Okay, you can download it from here. Right. But then when you submit, you want to go back to the quiz. Now, normally, even if you kill this tab and you open another tab and you do Moodle CSS, the login will stay. Yes, you should not have any problem. But all I was saying is, just in case, some unforeseen thing happens, once you downloaded the PDF, you have to do it only once. Just go back to is using the back button. So the tab, keep it open, keep it logged in. So after you finish, you scan everything, you just upload the PDF out. Because if you kill this tab, if I come back and so on, the same browser, it will still automatically log me in. And it's a continue the last attempt and so on. All I was saying, most 99% of the time, nothing will happen. But just so that to avoid any unforeseen thing, just keep the same tab open. You got the PDF, write your answers on paper, scan it, and just go back to that tab and just upload it. That's what I meant.
Okay, sir.
Any other questions? Why do Fibonacci F need the cascading cards? Okay, that's a big question. Okay, simple answer is because that's how decrease key works and the Fibonacci key properties are maintained. That I am not going to answer, and there is no clear answer for that also. You have to do a decrease key operation. That's how it works. Anything else? Anything else has come in chat other than this? No. Anything else? Okay. If not, let me go back. Let us quickly just discuss a couple of problems. Okay, so we'll kind of deviate from this, what we do every day, but these are some simple problems actually. We'll just discuss it and finish the class. So here is your first one. Okay, so in graph theory, there is this thing called the weighted cover of a weighted bipartite graph. It's an assignment of costs xi to each vertex I, such that for each ij, xi plus xj greater than or equal to wij, the weight of the edge ij. So input is a weighted bipartite graph, and you want to assign a cost to each vertex satisfying this property for every edge. Okay? And then the cost of the entire cover is the sum of the costs of all the vertices. So the question is, how do you find a weighted cover? That means such an assignment of costs with minimum cost. If I add up these costs assigned to each of the vertices, the sum is going to be minimum among all possible such ways I can assign this. There are obviously too many ways of assigning this. So what's the first thing that you notice? Anyone?
The equation is same as that from the weighted bipartite matching.
Right. So it is basically your x's are nothing but those levels that you assign for your Hungarian algorithm. Okay. That's the sum of those levels satisfying that basically at any point of time. Okay. And as I said, nothing falls from the sky, so it must be linked with something. And given that the levels are the same as this xi xj's, it must be linked somehow with the maximum weighted matching problem in bipartite graph that we have seen. So now can you think about an algorithm to find the weighted cover with minimum cost? We call it the minimum weighted cover. Anyone wants to try?
The Hungarian algorithm only gives the.
Yes. The algorithm
like
is
the Hungarian
trivial.
algorithm increases the labels only when it's necessary, like only when all the.
Right. So that argument you have proved.
That's not
The
a proof,
answer is
though.
yeah, that's not a proof exactly. So the argument is correct. The answer is trivial. Okay. So you basically use Hungarian algorithm, find the maximum weighted perfect matching. Okay. And then at that stage, whatever the labels are, that is the minimum weighted vertex cover. In fact, in many graph theory textbooks, so we did it with the matching, equality subgraph, and so on. They actually try to find the minimum weighted vertex cover and then say, oh, that is the maximum weighted matching. Just the other way around. Okay? So the algorithm is trivial, provided you know Hungarian, that you just call Hungarian algorithm find that gives you the maximum weighted perfect matching in the complete bipartite graph using those dummy edges and all. Okay, and then you basically dummy edges you can throw off anyway, and whatever the labelings are at those points on the vertices, that is the label. That is the minimum vertex cover, weighted cover. Sorry. Okay. Now, why is this the minimum weighted cover? Obviously, it's a weighted cover. Okay, because it will obviously satisfy this condition, actually satisfy equal. But then why is it minimum? Can it be lower, first of all? So can the minimum weighted cover be lower than the labels that you end up with at the end of Hungarian algorithm? What do you think? So to prove it, we have to show, if I claim that maximum weighted matching at that point, whatever the labels are, they give me the minimum weighted cover. I have to prove that the minimum weighted cover cannot be lower than this. It's actually minimum, nor can it be higher than this. So let's take one way. So can the minimum weighted cover be lower than the labels that I end up with at the end of Hungarian algorithm? So in the Hungarian algorithm, what do? You found a perfect matching, right? Something I do not know. Okay. Where did you find this perfect matching? In which graph?
On the equality subgraph.
On the equality subgraph. Okay. What is equality about equality subgraph?
Xi plus xj equal to wi.
Xi plus xj is equal to the wi. Okay. So that means you have got everything matched here. All the vertices are there. Okay. And xi plus xj equal to wij for everyone. So if the minimum weighted cover is anything less than that, you are going to break this condition. Right? Do you agree?
Yes, sir.
Everyone else? Let me hear a yes from somebody else.
Yes, sir.
Yeah? Okay. So it cannot be lower. Can it be higher? That I end up with levels of 100, but my minimum weighted cover is actually greater than that.
No, sir.
No, because
Why? See, the no is obvious. Just told you the algorithm works.
I mean, if we do have a greater minimum cover, then I mean the labels at the end of Hungarian algorithm is a cover,
Right.
And we just proved that the minimum cover cannot be lower than that. Therefore, it must be equal to that. If it is greater than that, then it's not a minimum cover, because you already have a lower one.
Actually, you want to prove it the other way around. Okay, not other way around, not exactly what you said. I think you got the idea. So one critical thing that you said, proper, absolute correct thing, that at the end of the Hungarian, what I end up with is a cover. Okay, now I end up with a maximum weighted matching, and it's a cover. Okay, and this cover has a value, let's say 100. Now, if the minimum was 120, okay, then this would not be possible. That means, put the other way. So what you said is correct, but I would put it this way when I prove by contradiction. that if the minimum was something higher than this, then this could not have been the maximum weighted matching, because the maximum weighted matching would have been higher than this also. Right? The argument is correct. Okay, I'm just kind of rephrasing it in terms of, you are saying this is cover, you're absolutely right. Therefore, it cannot be lower than that, which is what we proved kind of in the lower bound. But now we are saying why can't it be higher? It can't be higher because the maximum weighted matching would not be the maximum weighted matching, because this gives me a lower cover angle. So maximum weighted matching would be. So kind of same as what you said, just when we write it, probably have to write it next. But is it okay with others? Yes, no?
Sir, how do we guarantee that it is a cover?
Oh, that's because, remember what you did in the Hungarian algorithm. When you got this, you got a perfect matching, right? That means all the vertices are there in the equality subgraph. And say equality subgraph, that means xi plus xj is equal to wij at that time. And for the cover condition, I need greater than equal. I don't need greater than. So it's equal to, it satisfies this, so it's a cover.
Sir, hello.
Hello.
Yes, sir, but for example, if you have an edge which is like greater. Hello, am I audible?
Go ahead.
Yeah, sir, if you have an edge which is greater, but it is not included in the final map.
I agree, you have to prove that. Okay. I agree, you have to prove that. So sorry, I missed that. That could be a little bit involved. Yes, you are right. Okay. That something that is not in the equality subgraph, okay, for that also this condition is satisfied. And you can prove that easily if you look at the relabeling, how it is done. Okay, at the end you can show that for every edge, okay, this condition will be true for the next, the graph at the end of Hungarian algorithm. But I agree, you have to prove that. Yes. For those that are not there, this condition will still be satisfied. We'll not give you, okay, don't worry about the exam tomorrow. Everything is not about the exams, okay? So we'll not give you great, we understand this the last week that only you have done matching and all. Matching actually, so there is this huge bunch of practical problems called the assignment problems. If you search in Google called assignment problems, you will see, because there is so many times in practice that we have two sets of things and we have to assign one to the other. Sometimes the cardinality matters. Okay, you want to form the highest number of committees and stuff like that, as we have seen for where we use the application of flows in bipartite graphs and tripartite graphs and so on. Okay, sometimes it is basically the weights matter. For example, I want to assign jobs to machine with minimum cost and so on and so forth. Okay, so those are basically modeling problems. Other than that, it's more disproofs and stuff like that, knowing this algorithm and so on. So that's why I did not do too many, because we already have seen some of these problems in while doing applications of flow. Okay. So I did not put too many of these problems in the last moment in the tutorial. So the point that I am trying to make, why I said this, is for tomorrow's exam, we'll probably not do these proofs and stuff like that for matching and stuff. But yeah, you are right. You have to prove this one. But that proof comes actually from the, the Hungarian algorithm proof itself. So we're assuming that the Hungarian algorithm is correct. That at the end of that thing, this condition is satisfied for all edges out there. So this is the other thing. This brings me to one important point that I probably forgot to mention. I will probably send a mail out. Okay. So during the exam, okay, you can use anything that we have done in the slides. Okay. And Eddie, do we allow them to also use the tutorial problems?
Why not?
Yeah, last year we did.
Yeah, why not?
Yes. Okay. So anything that you directly use from the slides or one of the problems in tutorials, okay, you do not need to do them again in your exam. So for example, just as an example, last time I gave a problem that every k-regular bipartite graph has a perfect match. And suppose you want to use this result, because we have given you a problem where using this result will simplify your solution. So just use this result. You don't have to prove. Okay. So here also similarly, even though we did not do the proof of Hungarian algorithm, okay, so as kind of using that, basically that at the end of Hungarian algorithm, that condition will anyway be satisfied. So it will be a cover. So once again, I'll send a mail out again also, but just to be clear, anything that is there in the slides or any result that is directly there in the tutorials, one of the tutorial problems, if you need to use it to solve something in your problem, exam problem, just use them directly. You don't need to, we'll find out, okay? But make sure it's directly that problem on, not anything derived from it or the model is different or something, okay? I gave you an example of what I mean. Okay, any other question on this one? Okay, if not, the second one, I will just ask you to do it, okay? Again, I know there is a number of ways, you can do it very easily. So you have to show an example. That means you have to basically create the preference lists for those M1, M2, M3, M4 and whatever numbers you need, okay? Such and show that for given those preference lists, there exists more than one stable match. So typically in an exam, if we give it to you, we'll give you the preference list. We'll ask you basically, given this preference list, show me that 2 stable matches, so 3 stable matches. But here, it's a tutorial problem, so we're asking you to do actually create the preference list also. So this is a very standard problem. I don't need to give you a solution for this either. You just type more than one stable matching in Google, you will see like hundreds of examples. But this kind of clears up your ideas about what is stable matching is clearly, because Gale-Shapley just gives you one such stable matching. So it will be a good exercise if you create a preference list slightly larger, maybe 5 M's and 5 W's, okay, so that there are more than 2 stable matches, say 3 stable matches or 4 stable matches. So identify all of them and then find out which one is man optimal, which one is woman optimal. One of them will be. One of them will be man optimal, one of them will be woman optimal. And then if you want to go one step, but I understand the exam is tomorrow, but later on, you can verify that if you run Gale-Shapley with men proposing, you will get the same thing. With women proposing, you will get the woman optimal. So this one you try yourself. There is nothing to do. I think everybody will get it. Okay. So I am done for today. We deliberately did not want to give you too much today. And I think this week we have only 1 hour of lecture. It is mostly high school geometry. It's kind of a background for the computational geometry algorithms to come starting next week. So we'll finish up with graph theory now, start with computational geometry, NP completeness and all, and then we'll come back to algorithm design paradigms. So I'm done. Let me hear if there are any questions. See, Srijana, I'll have to work it out. Okay, I'm not God. So, so if you just give a long tree and you say size of the bound, maximum bound of dn equal to 2 exceeds, okay, I have to see whether what you are saying is correct or not. Actually, I cannot even see the numbers very well right now because it has got option 1, 2, 3, 4, 5, 6, 7. We consolidate the heap operation. Then 2, 3, 4 and 3. 1, 2, 3, 4, 5, 6, 7. So log 7 upper bound is 3, right? It's not 2. Am I missing something, Srijana? Hello? Right. Actually, it will be log 6 because we have 7 nodes and then 1 goes off. It will be 6. Okay, anything else?
Sir, can you discuss the sixth problem of last tutorial?
Sixth problem of last tutorial. Which was the problem?
Sir, I think the K regular bipartite graph.
Oh, okay. So it was the K-regular bipartite graph has a perfect matching. Right?
Yes, sir.
Yes. So I think just give me a second. So I think you give a 1-1 weights here. Okay. And you gave a 1 by K, 1 by K, right? All 1 by K's. 1, 1, 1. Let's see the solution I gave you. Just hold on a second. Yeah, anybody else? This is what I do. Anyone? Come on. So did anybody do it? Read it or not? They did do it. Let me hear a yes or no. So see, we give you the tutorials for you to try out. If not, look at the solution, understand. If not, ask questions and so on. Swamita asked it nice. But there are 42 other people. Have you looked at it, done it, not done it?
Yes, sir.
Done it.
No, looked at it.
Looked at it. How many could not do it? This is what? Hand raising. Okay, fine. Anybody else? So hand raising is yes or no. Vineet, that means you could not do it or could do it.
No, sir.
No.
Have to look at it.
We have to look at it. Now the hands are coming. Rest. Let me pick up somebody arbitrary. Okay. Girish, have you done it? Girish Kumar. So it's safe thing to put up the hand, right?
So does it make a difference? You send the solution anyway.
No, I did not send the solution fully.
No, I mean that is the hint. The crux was given.
Right. So have you solved it? So tell me, what is? See, if you assign the flows like that, sorry, the weights like that, capacities, then how do you find what is the final perfect match? That's what I'm asking. You know? To prove, either you have to prove that every vertex is matched to only one on the other side, okay? Or you have to actually show based on the flow that what is assigned to where is the perfect match. Has anybody done that?
So if I run the maximum flow algorithm, then
Right.
all the edges will be saturated.
Right.
But how
So-
will that help?
So I will do this. Okay. See all the okay. Let me not say it. Okay. I will do this. Okay, because this is not good. Okay. Some problems I give you complete solution. I give you solutions case. That's why I write because I still want you to think a little. And this obviously this problem will not be there in the exam, but this kind of a classic flow modeling exam problem. Okay. So why don't you guys think about it? Students are what? It's like 3:50 now. Okay. We'll end the class. Okay. 15 minutes down the line, I'll send you all the solutions. I will post it here. I'll keep Teams open. You can go do whatever you want. 15-20 minutes down the line, but I want you to try it. How does that sound? So this is a classic flow modeling problem. And then from there you have to show something. So fine, it's 3:48. Okay. I'll write the complete solution. Let's say at 4:10 max. That's enough time. Okay. ठीक है, करो. So whenever anybody is ready, you can tell. Otherwise, I will post it or talk about it.
Sir, I have an idea.
Go ahead.
Sorry, sir.
Go ahead. Go ahead. I said say.
Oh. So, sir, like if we have say two V vertices, so we have V vertices. Okay, fine. That is not necessary. Sorry, sir. I thought both the sides have to. Both the sides have the same card in it. Okay, fine. They
Both the
will have
sides
the same
have to
card.
have. They have to have. It's irregular bipartite.
Fine. So we have, so if we, the minimum cut value would be V times 1 by, like K times 1 by K. So that's like K 1 into V. It will be V. The minimum value, the capacity of the minimum cut will be V, because the minimum cut is when we partition, when you have the partition S, all the things on the left hand side, that's one partition. And the other partition will be T and the vertices on the right hand side. That will be the partition that causes the minimum cut, because if we have a cut that includes an edge from S to U or from V to T, then that will increase the value of the capacity of the cut.
So what you prove, okay, is first
therefore
thing
the
go ahead.
So the minimum value of the cut is, like, the cut value of the minimum cut is V, and therefore and that is exactly the maximum outgoing flow from S, and therefore we will have a perfect match.
Meaning?
With the flow, if the flow value is V, then we have a perfect match, right?
Yeah. So it's a small thing missing. I would not say missing, but you probably better make it explicit. Okay. Anybody wants to fill me up? Ishan here. Deep, you are almost 99% right. Maybe 100% if you write, I'm sure you write. Ishan? Your microphone is on. So you want to say something? Oh, okay. See, so Deep has almost said it. It's simple. See, the idea behind doing the 1 by K, 1 by K, 1 by K is to show that you can prove it very easily. Okay, because there are K total capacity going out of anything on the left hand side is 1. That means incoming 1 can be taken out. Total capacity coming into any of the nodes on the right partition is 1. So 1 can be brought in. So everywhere I can make the flow conservation. So it's easy to show that the max flow value is equal to 1. Sorry, V. Okay, in this thing. Now the max flow value cannot be more than V. Okay, even if I change the 1 by case to 1, right? Are you with me, or should I draw?
Yes, sir.
Anybody else? Should I draw?
I did not understand.
Okay, okay. See, what do you have to do? You have to show, if I want to show that all these edges get saturated in the max flow, I have to show whatever flow coming in here can be taken out, and whatever flow coming in here can be taken out. Okay. So what is the total number of edges going out of there? K, and each of them has capacity 1 by K. So this has a total capacity of going out of 1. So every one coming in can be taken out from each of those nodes. So I can maintain flow conservation at this node. Now question is, whatever flow coming out of all these nodes, can this push it out towards T? Same thing, there are K edges coming in into 1 by K capacity. Okay, so it can bring in 1, take out 1. Okay, so that says that I can have a flow that saturates all these edges and therefore saturates all these edges. Okay, which means my max flow value is a K regular bipartite, so I know both sides will have the same number of nodes. That's easy to prove. Okay, we discussed that in the tutorial also. So my max flow value is M. Okay, now since this is total M and this is total M, going out of S and going out of T, okay, even if I increase the capacities of these edges out here, okay, it's not going to affect the max flow value. Okay. So now let me make it 1, 1, 1, 1, 1. Okay, these things stay the same. And now let me run the standard bipartite flow. Okay. So I know there is a, see, by doing this 1 by k, I can prove that there does exist a max flow with value n, which means if I increase these capacities to 1, okay, and run the standard bipartite matching thing, okay, even then all these edges will get saturated. And now that they are saturated, because this has become 1, 1, 1 instead of 1 by k, 1 by k, only is standard bipartite matching. So you know each of them can only match with one of them, so you can find the perfect match. So this actually tells you automatically that a matching of size m exists. If you want to find the matching, you replace those 1 by k's with 1 and you run the standard bipartite matching. And by this 1 by k, you know that the matching of size m exists. And now the standard bipartite matching of size m is nothing but a perfect matching. Is it clear? Shomita?
Yes, sir.
Anybody else?
Hello.
But you see, as teachers, we are a little concerned. Okay. So there are 130 students in the class. Typically now tutorial attendance is down to 60, 70. Today it's even less because of the exams maybe, and I told it's a short class and so on. And only because Shomita asked the question, very nice of her, okay, that there are so many hands got raised that they are not seen. I will not give great looking solutions. I'll give you sketches because sometimes I want you to think some more. Algorithms cannot be learned by just reading a few algorithms. So please, the purpose of giving the solution a few days late that you will try. Okay? Then giving the solution is that you will verify that whether what you have done is correct or not. If you have not done, you can complete the solution. Please do so. Anyway, class is very little fun, both for you and us, because of this online thing. But is this problem clear?
Sir, hello.
Yeah.
Sir, in this, like initially when the capacity was 1 by k,
Right.
from each node we were pushing around k edges, each with
not around exactly k.
Exactly k edges, each with a flow of 1 by k.
Right.
And now if we just increase the capacity of each edge to 1, but
Right.
still now like we can make the same, like the flow can remain the same. Each node will still push out 1 by k and all those constraints will be satisfied. But that will not be a perfect match.
No, because now that I have made it 1, I will get an integral flow. Because all your capacities are integral now.
But the flow can be like decimal.
Huh?
The flow can be fractional also.
Right, but if I just apply, you remember the basic 4% property and all. Okay, if you have integral flows, integral capacities, okay, then you will find a flow with integral value of this. Otherwise, even your standard bipartite matching solving with flow will not work. Right?
Okay, sir, I got it. It will only increase by 1 at a time.
Right. Because you will find that augmenting path, all those capacities will be integral. So your minimum residual capacity will be integral.
Yeah, it will increase.
Yeah. So this is what I am, just an aside, this is what we miss actually. In class, these discussions actually can happen a lot more basically. Just think some more, give us more questions. Your queries, I hardly get 1 or 2 queries. So exams and all are there. I understand grades are important to you and all those things, but learning is also important. So please try things out from later on. Okay. But everybody present understands this, what happened here. Anyone has any confusion, you can ask.
So as for a constructive algorithm for this, can we do something on the following lines? Like for a one regular bipartite graph, the matching is trivial. Like the edges in themselves form a matching. So we need to just transform a k regular bipartite graph to one regular bipartite graph.
See what you are talking about. Okay, just take a look. So just type in Google the same problem, but without the word flow. Okay. So it's a standard property in graph theory that a k regular bipartite graph can be decomposed into k perfect matches. Okay. So if you take each of those perfect matching out, see, just think of a k regular graph. Okay.
Oh, I see.
And I take one perfect place, it becomes what? It becomes a k minus 1 regular graph.
Yes.
Okay. So what you are telling is exactly the same thing in reverse, the base case. So typically when we prove this in graph theory, we prove it that way by induction. Okay. So this was given here as just as an example of, because we are doing flow, just some brain teaser about, applying flow concept to it.
Yes, sir.
So one regular has a perfect matching, and then you assume k regular has k minus 1 regular has, then one perfect matching is same. Yeah. Any other questions on this? Okay, if not, we'll end the class here. Good luck to you all in your exams tomorrow. Eddie, nothing else to add, right?
Yeah, not much from my side. Yes.
Okay, then I will leave. Good luck to you all. If you have any confusion, any questions, you can still send me mail today and tomorrow before that.